Chapter 6, Section 3 is about AC. First, we'll talk about the properties of AC, and then we'll connect a resistor, an inductor, and then a capacitor to an AC circuit to see what happens to them. And then we'll combine all these three together in series combination and then in parallel combinations. And then we'll talk about some other properties that are possible in an AC. First, let's remember EMF that we got from an AC generator. EMF was equal to NBA omega times sine theta. NBA omega was the maximum value of the EMF. EMF is equal to E max multiplied by sine omega t. Instead of theta, I can write omega t. We talk about this one in section 1. And in this section, we will not use epsilon, we will use potential difference. So instead of EMF, we will be talking about potential difference. And if the potential difference changed as a sine function, the current also changed as a sine function. So the instantaneous current will be equal to maximum current multiplied by sine omega t. Let's have the sine graph for both potential difference and current. The upper side is for the potential difference. As time passes, v changes as a sine function. The red dot determines the maximum values of the potential difference. Current, again, it changes as a sine function, and as time passes, it is always changing, and the red dot again determines the maximum value. V is maximum only in an instant, and current is also maximum for an instant only. Let's have a graph for DC. We know that DC is always maximum. Let's have both graphs for potential difference and current. In a DC, the current is always maximum, the potential difference is always maximum. Both magnitude and direction in a DC is always constant. So V is always maximum, I is always maximum. Let's have a resistor that's connected to a DC source. DC source has a symbol of two lines. One of them is bigger, the other one is smaller. The bigger one is always positive, the smaller one is always negative. Let's say that the resistance is equal to 10 ohm, the potential difference is equal to 20 ohm. So the current automatically becomes 2 ampere. And the equation for power in a DC was equal to I times V, or I square times R, or V square over R. And as we calculate the power here, by any equation, you can use any of the equations, all of them will give you the same result, which is 40 watt. We'll use this number later. Now let's go back to the AC one. In one cycle, it is both positive and negative. So if we take the average for one cycle in an AC, it is equal to 0. So the average current for one cycle in an AC circuit is equal to 0. So if it is equal to 0, how is it when you connect a device to an AC circuit or an AC source, you have electricity and so on? How is it possible? It is because the power in a resistor does not wait for the average value. So it depends on the instantaneous value and the rate at which energy is converted in a resistor is directly proportional to the square of the instantaneous current and is independent of direction. So direction is not important. The square of the instantaneous current is important. Please remember that this is the definition of power. Power is the rate at which energy is converted. So we can say that power is directly proportional to the square of the current, and later in the power laws we will be using this equation. Let us convert this definition into equation. So it is saying that power is directly proportional with the square of the instantaneous current. So we'll be using I times R, but the current here is instantaneous. And the equation of the instantaneous current was I max times sine omega t. So let's square this, multiply by R. After some calculations, we will get an equation which is power equal to I max divided by square root of 2 in a square multiplied by R. This I max over square root of 2 is the current that is really giving us power in AC. So this part is the current that gives us power. And we will call this current as effective current or RMS current. RMS stands for root mean square. So IRMS or I effective will be equal to I max divided by square root of 2. So it is not the I max that gives us power in AC. It is I max divided by square root of 2, and we will call this as effective current. Now we can do some other calculations and get that the potential difference is also having an effective and RMS value. It is the same, which is Vmax divided by square root of 2. Let us connect the same resistor that we had a moment ago to an AC source, and let's see what happens when we connect it. The resistor is here. This is the symbol of an AC source. It is a sine wave inside a circle, and this is the resistance that we had a moment ago. Let's say that the V maximum is same as the previous one. The resistance is same as 10 ohm, so the current will be same. But which current is same? The maximum current will be same as the previous one because Vmax is same. So the current, the maximum will be 2 ampere. And let's have the equation of AC, which is I max over square root of 2 square multiplied by R, or we can say that I max square over 2 multiplied by R. When we enter the numbers, we get 20 watts. Previously, we had 40 watts in DC, now we have 20 watts. So the power that we get in AC is exactly half of the power that we got in DC. That is if the current that we have in AC, that is maximum, is equal to the current that we have in DC. So if I max of AC is equal to IDC, then power in AC is equal to half of the power in DC. We can rearrange it and say that power of DC is twice the AC. So P DC is equal to 2 times power AC. You can say that power of DC is twice of power in AC. When can we say these two sentences? That is only and only if the current that is maximum in AC is equal to the current in DC. The question here is this: how can I have power of AC to be equal to power of DC? The answer is if the effective current in AC is equal to the current that we have in DC, then we can say that power in AC is equal to power in DC. You can do the calculation. You will see that if the I effective is equal to 2 ampere in an AC source, then the power will also be equal to 40 watts. So we can define I effective as the current that is in AC that gives the same heating effect, because power is used for energy and it will give you the same heating effect if you have the same power. I effective is the current that is in AC that gives the same power, the same heating effect as the current in DC. From the definition of power, it was the rate at which energy is converted. We said that whatever starts with the rate means divided by delta time, and it is energy over delta time. We can rearrange it and say energy is equal to power times delta time. Instead of power, I can write I square R, I can write V square over R, I can write I times V, but I will prefer I square R for a moment. But the current that I should write here must be effective because it is the effective one that gives us power. If I write maximum, I have to divide it by 2 times R times delta time. Let us connect a resistor again to an AC source and see what happens when we connect it. We are talking about a pure resistor. Pure resistor means it has no self-induction. Coefficient of self-induction of a pure resistor is equal to 0. Let's have the resistor and let's have a switch and the source. We will connect an ammeter to see what happens to the current, and you will connect a voltmeter to see what happens to the potential difference across the capacitor. Ammeter and voltmeter, in order to be used, they need to be connected in different ways. Ammeter to be used must be connected in series combination. To use voltmeter, we need to connect it in parallel combination. This is the usage of ammeter and voltmeter. The one that you talked about and studied in chapter 5 section 3 is how to convert galvanometer into ammeter and voltmeter. So this one is different. The one that you studied in chapter 5 is different. Every source has the same equation: V max times sine omega t, I max times sine omega t. We are trying to find what is happening to these equations, expressions, as we connect a resistor, an inductor, and a capacitor. Before closing the switch, the ammeter is reading 0, the voltmeter is also reading 0. As we close the switch, the ammeter slowly goes to maximum. At the same time, the voltmeter will also go to maximum. So when we draw the graph for the current, we will get a sine wave. When we draw the graph for the voltmeter, we also get a sine wave. They are in phase. So if the angle of the V is 0, the angle of I is also 0. VR and IR. When we copy the equation, you'll get the same thing. So if one of them is omega t, the other one is also omega t. If the omega t here is 0, the omega t here is also 0. This is called as expression of the instantaneous potential difference and the current in a resistor. So if a question asks you about the expression of the instantaneous V and I in a resistor, directly you'll be using this one by finding V max, I max, and replace omega with the number that you find by the equation of 2 pi f. We have another important graph which is called as phasor diagram. If the angle of the current is equal to 0, the angle of the potential difference also equals to 0. They are always in phase. So we can say that VR and IR are always in phase, which means theta between them, or the phase difference between them, is always equal to 0. Resistance is equal to V effective over I effective, or V max over I max, or VR over IR. Resistance does not depend on frequency at all. Resistance in a resistor only and only depends on 4 quantities. The first one is the type of the material, the second one is the cross-sectional area of the wire that you have, and the third one is the length, and lastly temperature. As temperature increases, resistance also increases. So as length increases, resistance increases. As temperature increases, resistance also increases. But as cross-sectional area increases, resistance decreases. So it is inversely proportional with the cross-sectional area, because think of it as a wider road. The thicker the wire, the wider the road is for the electrons to pass through the wire. Let us connect a pure inductor. Pure inductor means resistance is equal to 0, so it has no resistance, to an AC circuit. So we have the AC circuit, we have the switch. Let's put the ammeter here and the voltmeter here. The equation for the source, which is V max sine omega t, same as the previous one, I max times sine omega t. For closing the switch, the current is equal to 0. So the ammeter is reading 0. The voltmeter is also reading 0. As I close the switch, the voltmeter goes to maximum, but this time the ammeter stays 0. Why is that? Because of self-induction. Self-induction creates a current in the opposite direction, which makes the ammeter to read 0. So the net current in the inductor at the moment of closing is 0, while the voltmeter is maximum. Because of self-induction, a phase difference has been created. Let's draw the graphs. So this is the graph for the current IL inside the inductor. So if the current starts from 0, the voltmeter starts from maximum. So let us draw the potential difference in the inductor. They are no longer in phase. There is a phase difference between them. So this is the maximum value, while the current is equal to 0. If we want to write the expression, we will get that if the angle in the current is equal to 0, the angle in the potential difference is equal to pi over 2. The VL is always ahead of the current. So we can say that if the equation of the current is omega t, the equation must be omega t plus pi over 2, because it is always added by plus pi over 2. It is always ahead. So when this is 0, this is 0 plus pi over 2. This is called as the expression of the instantaneous potential difference and the current in the inductor. Let us draw the phasor diagram for an inductor. We know that if the angle of the current is 0, the angle for the potential difference is 90 degrees. VL must be ahead by 90 degrees. So the angle here is plus pi over 2. So we can say that VL is leading the current by pi over 2. And the phase difference is plus pi over 2. Here we don't have any resistance, but we have an opposition to the current. Why do we have that? Because of self-induction. And any opposition that is not because of the 4 properties that we talked about in the resistor, which are the type of the material, the cross-sectional area, the length, and the temperature, is called as impedance. So now we have an impedance, and the impedance that we have inside an inductor is because of the self-induction, or it's because of the inductance of the coil. The symbol of impedance is X, and this impedance is self-impedance. It is equal to V over I, V effective over I effective, V max over I max, and VL over IL. We said that resistance does not depend on frequency, but the impedance here depends on frequency. unlike resistance. As the frequency increases, the change in the current also increases. If you change the current faster, would you have more self-induction or less self-induction? Of course, you'll have more self-induction. So if you have more self-induction, more opposition or less opposition, of course you'll have more opposition, which is more XL. So we can say that XL is directly proportional with the frequency. XL is directly proportional with the coefficient of self-induction. So we can write XL as omega times L, which is equal to 2 pi FL V over ampere, which is same as ohm. So the unit of impedance is still ohm. We can play with the units a bit more. Here we have ohm, which is XL, and instead of frequency, we'll write hertz. Instead of L, we'll write Henry. Or we can write the hertz as 1 over second. So we can write the ohm as Henry over second. It is time to connect the capacitor into AC source, but before that, we need to remember some very important points about capacitor from grade 11. So simply a capacitor is composed of two thin metal foils near each other, and we know that metals are conductors. They are conductors because they contain free electrons, or the electrons that are inside them are free to move. They don't contain extra electrons, don't confuse this. They have the same number of electrons and protons, but the number of electrons and protons are equal, but the ones that can move are the free electrons. So the charge of each metal plate at the beginning is equal to 0. So this is an uncharged capacitor. To charge this uncharged capacitor, we need to connect it to a DC source, or a battery is a DC source. One side is filled with positive charge, one side is filled with negative charge, and that's how we have potential difference across a battery. Let's connect one side to the positive and the other side to the negative. The positive side will attract all the negatives on the left side, and the negative side will send its extra electrons to the right. The uncharged capacitor was having 0 and 0 charge on each plate, so the potential difference across an uncharged capacitor is equal to 0. As we close the switch, the current goes to maximum, but at the beginning, the potential difference is equal to 0. After a moment, we will see that the right side will have more electrons, the one on the left will have more protons, positive charge. The left side will be positively charged, the right side will be negatively charged. As the capacitor is charged, the current stops, it becomes 0, so it acts like an open switch, and the potential difference in the capacitor will be equal to the potential difference in the battery, which is the maximum value. Every capacitor has a capacitance, which can be found by dividing the net charge that's stored across the capacitor divided by the potential difference. The capacitance is constant for a given capacitor. The unit for capacitance is farad. Whenever we have positive and negative charge, we have electric field between them. So we can say that energy is stored inside the capacitor as electric field. Now let's connect a capacitor to an AC source and see what happens. The symbol of a capacitor is two parallel lines. We have the source, we have a switch. Let's have an ammeter and a voltmeter here. The equation of the source will be equal to V max times sine omega t. Same for I instantaneous, I max times sine omega t. Remember that right now the switch is open, so the current across the capacitor and the voltage across the capacitor are equal to 0. This is an uncharged capacitor at the beginning. Both have 0 stored charge. As we close the switch, the current goes to maximum, but since there are no stored charges yet, the voltmeter will read 0. Because of the capacitor not being charged at the beginning, there will be a difference in the phase. As we draw the sine waves, when current is maximum, V is 0, and when V is 0, current is maximum. The VC is behind and IC is ahead. When IC is equal to 0, VC is minus 90 degrees behind. So the phase difference here is minus pi over 2. So let's have the expression. If the angle of the current is equal to 0, the angle in the potential difference will be 0 minus pi over 2 because it is pi over 2 behind. So we will add a minus pi over 2 to the expression. So these two are the expressions of instantaneous current and potential difference in the capacitor. the phasor diagram. If the current's angle is 0, we'll draw it on the x-axis. The potential difference will be behind by 90 degrees. We'll be drawing it on the lower side, which is minus y. So this will be VC, which is behind by minus pi over 2. So we can say that VC lags IC by pi over 2. Or you can say that the phase difference between VC and IC is equal to minus pi over 2. Here we also don't have any resistance, but we have an opposition, which is because of the source potential difference in the capacitor. We will call it again as impedance. The impedance is because of the capacitance of the capacitor, so we will call this as capacitive impedance. The symbol of impedance was X, and XC stands for capacitive impedance. Again, capacitive impedance will be equal to V effective over I effective, V max over I max, and VC over IC. XC will be depending on the frequency. But how? As frequency increases, the current changes direction less frequently. There will be more source charge across the capacitor. Lower frequency will give you more opposition because there will be more source charge. As a result, there will be more capacitive impedance. So we can say that capacitive impedance is inversely proportional with the frequency, and again it is inversely proportional with the capacitance of the capacitor. When we combine these informations, we get 1 over omega c, which is equal to 1 over 2 pi fc. Now let's connect all of them in series combination. So RLC in series combination, let's have a resistor, an inductor, and a capacitor, and connect all of them in series together with an AC source. This is resistance, inductance, and capacitance. Use Ohm's law for all of them. So V in the resistor is equal to I times R. V in the inductor is equal to I times XL. V in the capacitor is equal to I times XC. Whenever you see series combination, know that the current is same in all of the components because it's a straight road, so the amount of electrons that passes through every component is same. There are no side roads and it is a single straight road. So I total is equal to IR is equal to IL and is equal to IC. Now let's draw the phasor diagrams for each one to find the V total, because right now I cannot say V total is in the same direction as current, or it is plus pi over 2 or minus pi over 2, because it is a combination of all these and we'll be trying to find the equation for it. The current is in the x-axis. It is same for all of them, so I will be just copying this to all of them. V in the resistor is same as the current. They are in phase. V in the inductor was ahead by 90 degrees and V in the capacitor was behind by 90 degrees. Let's combine all these three together in a single graph because they are all happening at the same time. VR and VL and VL and VC, they are parallel to each other. When two vectors are parallel to each other, you can simply add or subtract them. Since VC is in the negative side and VL is on the positive side, I will say that VL minus VC. I will draw it on the positive side because I don't know yet if it is positive or negative. So the upper side will be VL minus VC. If VC is bigger, the total vector will be downward. VR is perpendicular to VL minus VC. When you have two vectors that are perpendicular to each other, you will be using Pythagorean theorem to find the magnitude of the total vector. So V total is this, and it will be equal to VR square plus VL minus VC square. We know the equation for the potential difference for each component, but what about the total one? The total one will be equal to I total multiplied by total impedance. Why would I call the total as not total resistance? Because I have two components that depends on frequency. So since we have two components that depends on frequency, the total will also be depending on the frequency. The total will also be called as total impedance and not total resistance. V total will be equal to I times Z. VR is equal to I times R, and VL is I times XL, and VC is I times XC in a parenthesis square in a square root. The current in all of them is same, so I can easily cancel all the current Z, which is equal to square root of R square plus XL minus XC square. I have three equations. The first one, which is the current, is same in all of them, and second one is the equation for V total, and the third one is the equation for total impedance. Pythagorean theorem only shows you to find the magnitude of the resultant vector. So what do we do about direction? we need to find the angle. Let's draw the graph again that we had a moment ago. Here we have VR, VL minus VC, and we have V total. We'll be finding the angle between V total and VR. It will be same as the angle between V total and the current. To find the angle for two vectors that are perpendicular to each other, we need to use tangent rule. Tan theta is equal to opposite over adjacent. Any component that is connected or attached to theta is adjacent. The other one that's not attached is called as opposite. VL minus VC divided by VR. We don't need tangent, we need theta alone. So theta will be equal to tan inverse VL minus VC divided by VR. Each V is equal to I times XL, I times XC, I times R. This is a series combination, so the current is same in all of them. Let me cancel all the currents. These are both correct, and they will give us the angle between V total and the current or VR. We will be connecting all of them in parallel combination. A resistor, an inductor, and a capacitor are all connected in parallel with an AC source. Whenever you see parallel, the potential difference is same across every component. So V total is equal to VR is equal to VL is equal to VC. Because every component, both ends are connected to the both ends of the source. Potential difference is measured across both ends. If both ends of any device is connected to a source, it will have the same potential difference as the source. Let's have the I total that's coming out from the source. So I total will be equal to V over Z. Here we have a separated part which IC will separate from I total and goes into the capacitor. And here we have another separation. The load is being separated, so IL will separate here and IR will go into the resistor. Unlike the series combination, which we had a straight rod, we have multiple rods that are being separated from each other. So we can say that IR is equal to V over R, IL is equal to V over XL, and IC is equal to V over XC. Let's draw the phasor diagram for each one, but this time we will be writing it in terms of V because they all have the same potential difference. So we'll be rewriting the phasor diagrams. In the resistor, they were in phase, so they were both on the x-axis. IR and V were in the same direction, but in the inductor, the current was behind because of self-induction. V was ahead, and in the capacitor, the V was behind, and I was ahead because of the stored charge in the capacitor. Now let us have all of them together on the same graph. IR is on x-axis. The one that is ahead is IC this time, and the one that's behind is IL. So IL is negative and IC is positive. So I will be deleting the lower side and I will be writing them as IC minus IL. Now I have two vectors that are perpendicular to each other. When we have two vectors that are perpendicular to each other, we'll be using Pythagorean theorem. This is the I total, and according to Pythagorean theorem, I total will be equal to IR square plus IC minus IL square, all of them together in a square root. I total is equal to V over Z, and IR is equal to V over R, IC is equal to V over XC, IL is equal to V over XL square in a square root. They have the same potential difference. They are all same, so I can easily cancel all of them. We'll be writing 1, 1, 1, 1. And that is the three equations that we have in parallel combinations. In order to find the direction, we need to have the phasor diagram again. And the angle that we need is always between I total and V total. In this case, V total is in the same axis as IR. We'll be using tangent rule to find the angle. Tan theta is equal to opposite over adjacent. And the one here that is opposite is IC minus IL. The one that's adjacent is IR. We know that adjacent is always attached to theta and opposite is not attached to theta. So we can write it as IC minus IL over IR. And if we rearrange the equation to have theta alone, it will be equal to tan inverse IC minus IL divided by IR. Can we write this equation as XC minus XL over R? Of course not. Why is that? Because IC is equal to V over XC, IL is equal to V over XL, and IR is equal to V over R. All of the potential differences are same, so I can easily cancel all of them. The equation will be equal to tan inverse of 1 over XC minus 1 over XL divided by 1 over R.
We have some important points that we need to know about series and parallel combinations, and that is if XL is bigger than XC in a series combination, then VL will also be bigger than VC because they are directly proportional. As impedance or resistance increases, the potential difference also increases in series combination. Automatically, the angle will be positive because VL is in the positive side, VC is in the negative side. Positive side will be bigger, the angle will be positive. But if XL is smaller than XC, then VL will be smaller than VC. They are directly proportional. Since VL is bigger, the negative part will be bigger, so theta will be negative. If XL is equal to XC, then VL will also be equal to VC. So they will be totally canceling each other's effects, and theta will be 0 here. In parallel combination, if XL is bigger than XC, then the current in the inductor will be smaller than the current in the capacitor because they are inversely proportional. Since IL is smaller, IC is bigger, then the angle will be positive because IC is in the positive side, so the bigger one is in the positive side. And if XL is smaller than XC, IL will be bigger than IC. The negative part, which is IL, will be bigger, so theta will be negative. If XL is equal to XC, then IL will be equal to IC, and they cancel each other's effect, so the angle will be equal to 0. In parallel and series combinations, we have a 0 angle in which the capacitor and inductor are canceling each other's effect. So this is a special case which is called as resonance. In resonance, XL is equal to XC in both series and parallel combinations. The notes that I will write in a moment, they are all correct for series and parallel combinations. So theta is equal to 0, Z will be equal to R because XL and XC will be cancelling each other. The only thing that remains in the total impedance equation is the resistance. And IC is equal to IL, VC is equal to VL, XL is equal to omega L, XC is equal to 1 over omega C. Rearrange the equation and we will get omega as 1 over square root of L times C. This is the equation for resonance angular frequency. If I want to find the normal frequency or linear frequency, omega is equal to 2 pi f, and divide both sides by 2 pi. Frequency will be equal to 2 pi times square root of L times C. So we can say that the resonance frequency is inversely proportional to the square root of the coefficient of self-induction. It is also inversely proportional to the capacitance of the capacitor. This is the only point that will be different for resonance in parallel and series combination, and that is Z, which is equal to R. Both Z is equal to R, but in series combination, the Z that's equal to R is minimum. Since Z is minimum, so you'll have maximum current. And in parallel combination, the Z that is equal to R is maximum. Since Z is maximum, the current will be minimum. Resonance has a very important application which is called as oscillating circuit. Oscillating circuit has been used in every device that works wirelessly. It is composed of a capacitor and an inductor. At the beginning, we will charge the capacitor by using an external source. The energy will be stored in the capacitor as electric field. Let's copy this. Let's say that the left side is positively charged and the right side is negatively charged. So there will be an electric field from positive to the negative one. As we release the system, the current will go from positive side to negative side passing through the inductor. So the energy will be converted into magnetic field because whenever we have a current in an inductor, we have a magnetic field around that inductor or the coil. And right now, the energy will be stored in the inductor as magnetic field. Because of self-induction, it will give back the energy to the capacitor, but in the opposite direction. So this time, the right side will be positive and the left side will be negative. The energy is being stored again in the capacitor as electric field. It will give back the energy to the inductor, this time as magnetic field again. But this time, the direction of the current will be opposite because the current goes from the positive to the negative one. The energy is being oscillated between the magnetic field and electric field. This oscillation, of course, has a frequency, for example, a billion times a second. We can find the frequency by using the equation, which is 1 over 2 pi in a square root L times C. We can say that the frequency is resonance frequency. Because of the resistance in the wires, some of this energy will be converted into heat, so it will be lost. So as time passes, the energy will decrease. This will lead to a damping oscillation. So it will slowly and eventually it will slow down and it will stop. But if we connect an AC source that has the same frequency as the system will be in resonance. It will continue to oscillate. By changing the capacitance of the capacitor or the inductance of the inductor, we can change the resonance frequency. That's how we can tune radio or TV. In some questions, C initial and C final will be given, so it is changing the capacitance of the capacitor, and it will ask you for the change in the frequency. Use this formula. Change in frequency will be directly proportional with 1 over C final divided by C initial. Or you can say that it's inversely proportional to the square root of C final divided by C initial. Or you can use and rearrange this equation as change in the frequency will be equal to in a square root C initial over C final. Another very useful device is called as transformer. Transformer is a device that is using mutual induction to increase and decrease potential difference. Let's have the picture of the transformer. As you see, it is similar to the mutual induction, which we have two coils and we have an iron core. The input one is called as primary, the output one is called as secondary. If you have a charger, which is a transformer, you'll be connecting it to the outlet at your home. So you are connecting the primary to the outlet. The input is V1, the output is V2. The change in flux in the primary is equal to the change in the flux in the secondary. Because if I change the flux in the primary 10 times a second, I will have the same change in flux, which is 10 times a second in the secondary coil. Let's remember Faraday's law for induced EMF, which was minus n change in flux over delta time. And I need delta flux over delta time alone, so I will be dividing both sides by n. They will cancel each other. Change in flux over delta time is equal to minus V over N. Instead of epsilon, I will be writing it as potential difference. So I will not be using EMF here. I will be using potential difference. V over N is equal to V over N, and V1 over N1 is equal to V2 over N2. Let's rearrange this equation. I will have V2 alone because that's what I'm trying to find. V2 will be equal to N2 times V1 divided by N1. That should be N1. N2 over N1 is called as conversion ratio. If N2 is greater than N1, then N2 over N1 will be bigger than 1. V2 is bigger than V1. Whenever V2 is bigger than V1, this is called as a step-up transformer because we are increasing potential difference. And if N2 is smaller than N1, then N2 over N1 is smaller than or will be smaller than 1. As a result, V2 will also be smaller than V1. Since V2 is smaller than V1, this is called as step down transformer. Change that to N1. Efficiency of every transformer is between 90% to 99%. This shows that there's a power loss or energy loss due to some reasons. Power is lost in a transformer because of two reasons. The first one is because of the resistance in the wire of the windings. The second one is because we have a change in flux and we have an iron core, so there will be eddy current produced in the iron core, which produces heat and current and string magnetic fields. This will lead to power loss. So we can say that power is also lost due to small currents induced by the change in the field and the flux in the iron core of the transformer. Let's have some other details. We know that in an ideal transformer, power in the primary is equal to power in the secondary. Power is equal to I times V. Please remember that transformer doesn't have the ability to increase power. In an ideal system, it can transfer all the power to the secondary one, which is in an ideal transformer. So if V increases, current will decrease here, and vice versa. If V decreases, current will increase. So I want V1, I2, V2. Let's copy this one more time for the step-down transformer, and we will see that in a step-up transformer, V2 is more than V1. Since V2 is more than V1, I2 is less than I1, and V1 is less and I1 is more than I2. In the secondary of a step-down transformer, V2 is less. That's why it's called a step-down. So I2 is more than I1, and as a result, V1 will be more, I1 will be less than I2. Here I have 2 points, the primary of a step up and secondary of a step down. The current is more than the other winding or coil, which causes more power loss. Because power is lost because of 2 reasons, we talk about that. One of them is because of the resistance in the winding, and to increase the efficiency of this transformer, we need to decrease power loss, which is equal to I square times R. How can we do that? By using a thicker wire, because a thicker wire has more cross-sectional area, and as the wire gets thicker, resistance decreases, and that is because a thicker wire has lower resistance. So we can say that in a step-up transformer in the primary coil, the current is more. Since the current is more, we need to use a thicker wire. So a thicker wire is used in the primary of a step-up transformer, and in the step-down transformer, the secondary coil has more current. So we need to use a thicker wire in the secondary coil of a step-down transformer to decrease power loss. The last topic is energy transfer. Let's have a dam that is producing electricity, and let's have a town that will receive this electricity. The generator in the dam will produce a potential difference of 5,000 volt and a current of 1,000 amperes, and we will transfer this by means of a wire that has a very, very low resistance of 10 ohm. 10 ohm is very low for a very long distance. So the question is, what is the power received by this town? Please remember that power sent is always equal to I times V, and power lost is always equal to I square times R. The current here is the sent current. Let's find the power sent first. This is equal to 1,000 amperes multiplied by 5,000 volts, which is equal to 5 times 10 to the power 6 watts, which is 5 megawatt or 5 million watts. Power lost is equal to I square times R. I is 1,000. Let's square it, multiplied by 10, which is equal to 10 times 10 to the power 6 watts. So the power lost is 10 megawatt. And power received is equal to power sent minus power lost, which is equal to 5 times 10 to the power 6 is the sent power, and 10 times 10 to the power 6 is the lost power. The answer will be minus 5 million watts or 5 megawatts. So simply the town will be in debt and will not receive any power. So how can we solve this problem? We can solve this problem by decreasing the power loss, because that's what is preventing the town from getting any power. And power loss is equal to I square times R, but the resistance is already low, so we cannot do anything about it. We can only do something about the current. So we need to lower the current so that the power loss is also lowered. Because if we decrease the current by 10 times, the power loss will decrease by 100 times. So the power loss will always decrease by the square of the amount that we decrease the current. We can decrease the current by using a step-up transformer. We will send this electricity by means of high voltage and low current. Let's have a step-up transformer between the dam and the town. Let us step up the potential difference to 500,000 volts, and let's see what is the current here. The power is 5 times 10 to the power 6 divided by the new potential difference that we will send the current with, which is 5 times 10 to the power 5 volts, and the answer will be 10 amperes. Let's find the power loss now. 10 is the sent current, square it, multiplied by another 10, which is the resistance. The answer will be 1,000 watt. We have decreased the power lost from 10 megawatts to 1,000 watts. Power received is equal to power sent minus lost. The sent power is 5 times 10 to the power 6. The lost is 10 to the power 3. So the power received by the town will be equal to 4.999 times 10 to the power 6 watts. Nearly all of the power is received by the town just by making this small difference by using a step-up transformer and increasing the potential difference and decreasing the current. And we can find the efficiency of this power transfer by dividing the received power to the sent power, multiplied by 100 to find the percentage, which is equal to power sent minus power lost divided by power sent. Power sent, remember that it is always I times V. Power lost is always I square times R, and the power sent again is I times V. Multiply the answer by 100 to get the percentage of the power that is received by the town. That is called as efficiency of a power transfer.